this opportunity to introduce a new member of the high energy division, Derek. Would you like to briefly introduce yourself?
Yeah, so those who haven't met me yet, I'm Derek Schellenberger. I just arrived from Bonn, Germany last week, and I finished my PhD on cosmology, and now I'm going to work with Jan, Larry, and Ewan on galaxy clusters and groups. So if you want to talk to me, I'm in the same office as Jon and Lorenzo. So.
234.
Ah, yeah. I don't know the number yet.
Thank you. Today our first speaker is Marilu Gendron-Marsolais, and she's a graduate student at the Université de Montréal, University of Montreal in Quebec, Canada, and where she is working with Professor Julie Halasik-Bohondo. And she has been visiting Center for Astrophysics for half a year. And here she's working with Dr. Rothkraft. And before she came here, she has rich experience in radio observations. And since she came here, she has been equipped with new skills and experiences of X-ray observations. And today she's going to talk to us about radio and X-ray observations of field galactic systems.
Thank you, Yuan. Congratulations for pronouncing my name. So today I'm going to talk about uplift, feedback, and buoyancy. So everything you want to know about radio load dynamics in two systems, so two objects I've been studying since the beginning of my PhD. So in summary, I will briefly introduce what I mean exactly by dynamics of the radio lobes and what I mean also by AGN feedback. But the main part of my talk will be on initial results on the analysis of the observation on two objects, like I said. So first, a group of galaxy with M49 on the center. So I've been working on that galaxy group here at the CFA, so on something like 400 kiloseconds of Chandra observation on this object. And second, I will present a new VLA low-frequency observation of the Perseus cluster. So let's begin by an introduction. So, as you know, clusters of galaxies are the largest gravitationally bound structures in our universe. They extend to megaparsec scale and contains hundreds to thousands of galaxy group are just smaller and more common. So the space between those galaxies is filled with a hot diffuse gas called the intracluster medium, the ICM, which will emit in the X-ray. The thing is that as this gas will emit in the X-ray, it will create a radiative cooling, and a very high star formation rate is predicted like that. So this is called the cooling flow problem, because this very high star formation rate is actually not observed. So instead, it is believed that the AGN feedback will prevent this cooling by compensating those radiative loss by radiation and outflow produced by the accretion onto the supermassive black hole of the central galaxy. So this is the AGN feedback. And in the particular case of the mechanical AGN feedback here that I will talk about, so the signature, we see a signature of this mechanical feedback. The signature of the interaction between the radio jets and the ICM, the intracluster medium. So this is directly observable into the X-ray images. As you can see here, for example, in the Perseus cluster, you will see those large cavities. You can see also in galaxy group in this example here. And so those are actually created when the jet would just push the intracluster medium and create cavities into the X-ray gas. And so we'll see those kind of cavities. So AGN feedback is the generally accepted solution for the cooling flow problem, but there's still a lot of open question about the detail of this mechanism. For example, how the energy is actually transferred to the ICM. How does that work? Is it by through shock or turbulent heating or sound wave? Or maybe all of this. So it's not clear yet. And to try to answer to those questions, one of the possible things we can do is we can study lots of individual nearby cases. For example, those three cases here. of nearby object that will provide the sensitivity and the resolution to see really the detail on how the AGN feedback is working. But before to move on, I want to be a little bit more specific about what I mean by radial lobe dynamics. So in a very schematic and simplified explanation, the formation and the evolution of the radial lobe will proceed in kind of three main steps, I would say. So first, what happens is just, so what I call the jet phase, is just that the jet would just drill through the ICM, creating a bow shock. And then eventually the plasma, the relativistic plasma transported along the jet will begin to inflate the lobe in a supersonic expansion as the internal pressure of the lobe will push the gas aside. And this is how the bubbles are created, radio bubbles. And so this will push the ICM gas aside and will create some kind of a shock shell of gas around the bubble. And then eventually, once the expansion of those bubbles became subsonic, if we consider that it does that under a stratified atmosphere, under the influence of the gravity, then once the expansion velocity of those lobes will go below the buoyancy speed, the lobes will just detach and float away as a rising air bubble into the water. So this is a picture here compared to the Perseus cluster, where you can see in X-ray here one of the cavities. So it's the same kind of thing, but those are like 10 to the 22 times bigger, but it's the same principle. And also I want to mention that once those bubbles are detached and float away, like the population of electron will age as it loses energy, as it emits radio, and eventually we won't see it at higher radio frequency. We will only see it at lower radio frequency, and eventually we won't see it at all. And this is why we call those detached bubbles far away from the center, we call those ghost bubbles. So in order to really understand the details of the AGN feedback, what we need to do is to study both in X-ray and in radio those kind of nearby cases. For example, the Perseus cluster here again, with the inner cavities in pink, you see the radio emission, so you see the radio lobes. And in kind of bluish here, you can see the X-ray, so you can see the impact of the lobe onto the intracluster medium. So having those two kind of sides, you have a better chance to understanding what's going on. So I will now move to my first case that I've been studying, so NGC 4472 M49, which is right here. So it's the dominant member of a group of galaxies here, falling into the Virgo cluster, so you have M87 here. It's about 4 degrees south, like that. So it's a X-ray bright early type galaxy. It's actually the most optically luminous galaxy in our local universe. It's even brighter than M87 in the optical, but it's fainter a little bit in the X-ray. So here are my data. So it's 300 kiloseconds of new Chandra data for a total of 380 kiloseconds. So we are dealing here with about 1 million count, and the gas temperature is around 1 keV. And in this image, so this is the raw image of the combined data set, and in this image you can already see maybe like the presence very close to the center, so like 5 kiloparsec of some kind of cavities very close. But if I show you the background subtracted, exposure map corrected image smoothed and removing the point source, now the cavities becomes very clear, as well as those rims of enhanced emission just beyond the lobes. And here it is with the 1.4 gigahertz VLA radio contours, and you can see how well the radio contours fits, the radial lobe fits in the cavities. And to enhance the deviation from the surface brightness, the average surface brightness profile, this is the fractional residual image, where you can see lots of structures in the gas. And here again, with the radio contour. And oh yeah, one thing I want to mention here is that NGC 4472 is not a powerful radio outburst. So the flux density here in the lobes are about 8 milligensky. The center is about 0.2 Gensky here. And And so we want to understand what are those rings of enhanced emission just beyond the lobes. We want to have some kind of explanation to that. And there's like two possible explanations, as I told you just before. So it can be shocks, so AGN-driven shock. If the bubble is inflating supersonically, then it will create a shock right here at the border. Or if the bubble is rising buoyantly and not supersonically, then this could be an uplift of gas from the center bring up there. So to find out, what we did is we extract the spectrum from lots of different regions around this east lobe here. And I'm just showing you one example here of what we've been doing. But basically, each time what we found when we found the temperature is that this material here in the rim is colder than the material outside. And so that means that those rims of enhanced emission cannot be shock. Instead, if there is like low temperature and higher density, that means that it has lower entropy and it comes from the center. So we don't have shock, we don't have supersonically inflated bubble. We have instead gas uplift from the center, dragged out by buoyantly rising bubble. And also I wanted to show you the soft bend image when you can see the rims, and those will disappear in the hard bend. There's also a very another very interesting structures that have been found in this previous observation analysis of XMM observation. And so in this paper, they found, I don't know if you can see it well, but it's pointed by those green arrows here. So what I've been showing you before, so remember it was like 5 kiloparsec or something like that. So here it's at much larger scale. So those filaments here pointed by the green arrows are like something like 25 kiloparsec long. And so like much further from the center. And once again, those are only visible in the soft band. They disappear here. So one thing that those kind of filaments could be is that they also could be gas uplift from the center, this time from detached bubble rising way further out than what I found. So there might be bubbles here, radio lobes here, but there is no gigahertz radio emission filling those lobes that have been found yet. But I will probably work on getting low frequency multi-configuration VLA data to see if we can find some radio emission here. That would be interesting. So going back to the Chandra data that I've been working on, so we can ask ourselves, okay, so if this is uplift gas, what kind of energy it takes to drag this amount of gas, for example, in this yellow region here, from the center up there, working against the gravity. And this has been done before in Reynolds in 2008 for a cluster of galaxy. And if we consider here some kind of half of an elliptical shell, something like that, so I found that the energy required to lift this amount of gas is about 10 to the 55 erg. And now we can compare this to the energy injected in the cavities by the jet. And this is a very common thing to do when we have X-ray cavities like that. So basically, the common way to do this is by calculating the enthalpy of the radio lobe, which is basically the sum of the work needed to inflate the lobe plus the thermal energy of the bubble. And that gives us the 4 PV right here. And once again, I've got something like 10 to the 55 erg. So within the uncertainties on those numbers, those values are comparable. And we can also compare this with two other cases here, so Hydra A and Abel 4059. So the case I based my calculation on in 2008. So those are two like big clusters of galaxy. So you can see they are much more powerful outbursts than in our case here of group of galaxy. And what we found out is that the ratio here of the uplift energy compared to the energy injected into the lobes is much higher in our case than in those two cases of clusters of galaxy. So this is, in a big summary, the main result, I would say, for now, for my analysis on NGC 4472. And now I move on to the other case I've been working on, so the Perseus cluster. So I've been working on X-ray, but for the Perseus cluster, I've been working on those radio data. So yeah, Perseus clusters, you can see here apart, is one of the prototype example to study the radio lobe dynamics. And this is the famous 1.4 megahertz image of the Perseus cluster, so lots of things going on. You might first see this kind of spiral structure here in the X-ray gas. And this is probably caused by a minor ongoing merger. So there is like some kind of a chain of big galaxy here that you can see in the optical. And this will cause this kind of sloshing motion. If we zoom into the center, you will see those inner cavities here as well as outer cavities. And so I will mostly work on those kind of outer cavities and see if I can find radio emission in it. So what about the radio emission? Yes. So here's the same image I was showing you in the X-ray, overlaid with radio contours. I will show you different radio contour at different radio frequency, beginning at the lower radio frequency, 74 megahertz. So here in this image, you can see that the radio emission fill the inner cavities as well as the outer cavities. If we move now to 235, what happens is there is less emission in the ghost cavities. And then eventually, at 330 megahertz, there is a little bit of emission. And finally, at 610 megahertz, here, the contour you can see here is not related to the emission into the lobes. So those are related to the structure called the mini halo, which is a structure found in couple cluster. It's a large scale, very faint radio structure that you can find. And there's the different spectral index from the radio lobe. And so we can differentiate it from the radio lobe that way. So if we put that all together and build the spectral energy distribution in the case of the ghost bubble here, so we find this kind of shape. And so with those points here, so in particular with those images, we found that the spectral energy distribution will steepen from this parallax at a break frequency of around 235 megahertz. And so in order to conduct a spectral aging analysis of this ghost cavities here, we need to populate this frequency range to add points here to better constrain the curvature and to better constrain the aging model. And this is great because the new JVLA P-band falls exactly in this frequency range. So we got 13 hours of JVLA data from a 2013 P-band share risk proposal, and I've been working on those data. So it's really challenging because first, because it's at very low frequency, so there's lots of radio frequency interference. So about 60, maybe even more, of the data set needs to be removed from the data set. And also because Perseus is very, very bright at this in radio at this frequency, and what we want to see is those very faint radio emission, like for example the mini halo and the emission in the lobe. So we are dealing with a very high dynamic range. So I was just gonna show you. So it's still work in progress, but this is one of the best image I have now for the B configuration. So you can see there is a little bit of artifact of ripples, a little bit that need to be removed. And I must say that this is only for one spectral window. So there is 16 spectral window in this band, 15 megahertz each, and this is an image of only one spectral window. So the data set is so large that for now I'm just concentrating in one spectral window, trying to get the best image possible. But it's good because the RMS is already an order of magnitude better than the previous image of the Perseus clusters at this radio frequency. And you probably noticed those really nice narrow angle radio galaxy, so NGC 1265 and IC 310 here, which are really, really interesting. I will study more, that's for sure. And if we zoom in the center here to see the lobes, so this is the emission, the image I just showed you with the contour, and this is on the X-ray image, and this is compared to the previous VLA image at the same frequency. So you can already see that emission goes way further than in this case, and it will fill entirely the radial lobes here, the outer cavities, and also you can see the mini halo structure that will emerge. And since the p-band is so large, it will be very easy to make a spectral index map of that and be able to differentiate the emission from the lobes from the mini halo. So one thing that is nice also about the mini halo, so you remember this kind of spiral structures I was showing you before. So you can see that the mini halo is kind of following this structure, which makes sense because sloshing motion, like trace in a way, like the place in the cluster where it's more turbulent, and this turbulence will should be able to reaccelerate the particle and cause the presence of the mini halo. There's also this nice spur of emission that corresponds with some kind of X-ray filaments here, also seen in H-alpha. So that's my result for the Perseus cluster. So I will conclude. So I've been presenting the analysis on radial lobes in 2 nearby cases. So in the case of M49, we've been detected very clearly cavities, as you have seen, and as well as a significant uplift of gas from the center. So those new Chandra data really help us to understand what's going on in the center of this group of galaxies. And hopefully with radio data, we'll be able to have even more better understanding. For the Perseus cluster, it's still work in progress, but we already detect emission in the ghost cavities, as well as the presence of the mini halo, which is very clear in our data. So I hope I convinced you today that this really detailed analysis will help us get a better understanding of the aging feedback. So thank you.
Questions from our
Have you looked if magnetic fields can play a role in the dynamics here, or do we?
What do you mean in general?
In the general structure and evolution of these rocks? We see similar things in other places that are controlled by magnetic fields.
Yeah, well, actually, well, one thing I can mention that I've been reading about in the case of the Perseus cluster. So I've talked about this kind of filaments here, and it also corresponds to very well to a H-alpha filament. And actually, there's lots of H-alpha filaments that you can see in the composite image. There was like lots of things, and those are very thin. And I think I read one paper saying that there must be like magnetic field to like create those kind of structure. But yeah, so that certainly play a role. Yes.
I think it's because it's quite striking that actually the big ghost cavities are not filled actually, the one below. Well, actually the enhancement is on the H-alpha filaments, which is there also like star formation in those filaments? Because of course radio emission also creates a star formation. So
What do you mean?
The brighter filaments, right? You see like
here?
on top and in the bottom, yeah. Because the radio emission is clearly enhanced on those brighter patches of X-ray emission, right? As you said.
Yeah.
In the north both and in the south. There's this extra radio structure sitting inside.
Here?
Yeah, exactly there. So, can that also be from star formation?
I don't know.
The question is there star formation in those filaments? Is that known from optical or whatever observations? Because I was wondering.
I don't know.
Because it's quite striking that because it's quite unusual to see this actually. So that was I'm wondering why.
Yeah, I don't know.
So I was actually going to, now that you brought that up, I was going to ask you the question back. Could one then expect to see a difference in spectrum between the mini halo and the region
Yeah.
star formation?
Yeah.
So one could
Yeah,
look
but-
test for that in particular.
I would actually then more expect to see this at high frequency of the star formation. So then it would go back to like 1 gigahertz because star formation still has flat spectrum, or even like 3V emission you expect there. So you would may want to go even higher frequency. So on the other hand, if magnetic field is enhanced, you can also enhance the radio emission. But it's a bit striking that it's only a low frequency because then you need the spectrum in order to.
Yeah.
So that was sort of my question is, so you see the nice radio emission from the 2 inner lobes, but there's really truly no hint from those other 2 darker features that are further away are
There's-
those two features really cavities, or could they just be something left over from the analysis
Uh,
of preparing the image?
I think, I don't remember exactly, but if we go back to,
Yeah, but you do see the radio emission that far out, right?
so, sorry. Yeah, so I think there was like other cavities, right?
Yeah.
So
Yeah.
there is like those 4 here,
Yeah.
and then I don't think that this one is considered as a cavity. I think this one is, there is 1 here and like 2 here or something like that, if I
So
remember well.
The one at the
So-
top, that was part of that big, huge feature.
Yes,
that
this
goes
one.
almost all the way around.
Yes, yes, this one here.
Yeah,
Yeah, it's very, very large.
yeah.
I don't know.
I should say that would never be deflected in these observations because it's resolved out. Because the resolution is too good of these observations to see this
Yes.
thing, so you would have to add the other data.
Like deconfiguration, yeah,
Okay.
will help. Yeah,
The
see,
VRA,
yes.
So one question about 4472. If you
Yes.
go back to the last slide, where you were showing the energy fraction here.
Yes.
Let me say this one. So as I see these other two examples.
Yes.
Talking about quite different scales here.
Yes.
So does it have to do anything with the different ratios?
Well, maybe I don't know. Maybe, but I haven't found like some the similar kind of example to compare, like the similar kind of thing. I don't know. That would be an interesting thing to check. Yes.
Any other questions for Marilyn? Any questions up there? If not, let's thank Marilyn. Actually returning to
Yes.
Montreal in a few days, so if you want to talk to her, please hurry. And she's also in the same magic office.
Yes.
Please choose her.
That's all.
Our next speaker is Kamen Kozarev. Kamen is a postdoc at the Smithsonian Astrophysical Observatory, and technically his position is NASA Living with a Star Jack Eddy postdoc fellow. And Kamen grew up in Bulgaria, and then he did his bachelor's degree in William College in Massachusetts. And he got his PhD degree in Chandra from Boston University. And today he's going to talk to us about how particles are accelerated from 10 keV to hundreds of MeV near the sun. Thank you.
Okay. Thank you very much. Oh. All right. Can you hear me? Great. Okay. Switching topics completely, I would like to talk to you about early stage solar energetic particle acceleration in coronal shocks. So let me get right into it. Solar eruptions, in particular coronal mass ejections or CMEs and flares, are some of the most energetic events that occur in the solar system. And they're prime manifestation of solar activity. They release significant amounts of energy into the heliosphere, and they also modify the entire heliosphere. So what is a solar eruption? So canonical eruption, first let's look at this cartoon here. Well, usually you have a prominence that's kind of lying over some magnetic fields, and when the eruption occurs, usually caused by reconnection processes, that cut basically the tethers of the magnetic fields overlying and underneath the prominence, it's ejected. So the magnetic field energy stored in the twisted fields is transferred into kinetic energy. On the sun, it manifests as what are known as H-alpha ribbons, X-ray loops, and collectively as a flare, which is the enhanced emission at the high frequencies of light, and then the prominence itself turns into a coronal mass ejection when it's ejected from the sun, driving a pileup of plasma in front of it, basically sweeping through the solar wind and the coronal material, and very often driving a shock. So I'll show you an example right now of a very spectacular eruption, which you may have seen, but just to mention that most of the observations I'll be talking about today are from the Solar Dynamics Observatory, which is a wonderful mission to observe the sun, and specifically from the Atmospheric Imaging Assembly Instrument, which are these 4 extreme ultraviolet telescopes that just stare at the sun all the time, and they provide us amazing data. So, this is the eruption from June 7th, 2011. So you can see, if you didn't know, this is the sun, the size of the sun, and so you can see how big this eruption is, one of the biggest eruptions of this solar cycle. It 2011, no, is kind of on the uprise of solar activity. Yeah. So it's very similar to this picture where you have a prominence being ejected, or a flux rope also, or as it's being ejected, it turns into a bundle of field lines. And so there's this catastrophic release of energy, and here you can even see some of the material falling back down. Okay. So something else that's very interesting that we've been able to observe for the past, I would say 20 years, are these so-called EUV wave, or extreme ultraviolet wave, that you can see in this movie of the same event, except it's a base difference image, or rather a running difference image. But you can see these fronts that are bright fronts showing up in the difference images over time. And we can measure their kinematics, and they seem to be moving quite fast, hundreds, between 300 and maybe even 1,000 kilometers per second going out. And that is important, since these are believed to be compression and shock waves that are driven by the ejection that's leaving the sun. And also, it's possible, it's very likely, and many people have done modeling of this, is that there's this sweet alpha and speed dip, kind of low in the corona between 1 and 3 solar radii. So that's also another way that we can kind of tell that these are shock waves. So keep that in mind. Now, when the CME goes out into interplanetary space, as I said, it disrupts the environment significantly. And this movie shows you a model of the evolution of a coronal mass ejection out to beyond Earth, beyond Mars even. So you can see these are maps of the density scaled as 1/r². And this is the Parker spiral field lines, and the solar wind just going about its business, sun rotating, and then the CME comes about and just destroys the whole spiral pattern. And what's interesting to note here is that you can see the extent of the CME in both longitude and latitude here is gigantic. Another thing it does is it modifies the magnetic field line connections. In other words, the connectivity between the sun and other bodies in the solar system. Now, this picture here, which looks terrible on the screen, shows you a top-down view of a CME in progress. And as I mentioned, these coronal mass ejections, they can drive shock waves if they're moving faster than the local medium speed, which we take to be the alpha speed. So here you have the sun in the bottom, you have the driver, the flux rope, and eject. So the CME, the body of the CME, then you have some compressed wind, the shock front, magnetic field lines, and energetic particles are thought to be accelerated at these shock fronts, and then spread out in the solar system, basically surfing along these magnetic field lines and taking advantage of this great connectivity that the CME provides. They're also thought to be flare-accelerated particles in reconnection processes during the flare, very low in the corona, but they have different signatures usually than the shock-accelerated particles. Until very recently, people thought that that there were two types of energetic particle events. In other words, when you put a spacecraft that measures the particles in situ in interplanetary space, just counts the particles coming in, and you look at the fluxes of particles over time at different energy channels, they thought that they would observe an impulsive event, which is a small spiky-like increase of the particle fluxes, and usually protons, by the way. And then there were these gradual events when you have a large gradual increase of the particle fluxes, and when the shock passed by the spacecraft, let's say Earth, near Earth, you would see a spike in the particle fluxes. Now, that's great, except since we've been able to observe routinely these EUV waves and with coronagraphs to look at what's happening closer to the sun, we see that in many cases you will have a solar event going off, a coronal wave, EUV wave, and then very little time after that, you would see a large increase in the particles over time at 1 AU. So this sort of begs the question of, are these particles accelerated in interplanetary space, or maybe are they accelerated closer into the sun? By the way, when I talk here about the gradual increase, I mean that the idea is that the particles are accelerated as the shock is moving through interplanetary space. But it may not be the case, and so you may have acceleration close to the sun where there's a stronger shock, but then the CME may decrease, decelerate, and so may not be accelerating particles anymore. So there's this blur in between these two types of events. Okay. And next. Okay. So people have started looking at the dynamics, the dynamics, the kinematics of the eruptions and CMEs and how they behave close to the sun. So many CMEs, it turns out, that start very low in the corona, and they accelerate to near their final speeds very close to the sun within 3 or 4 solar radii. So, for example, Bain et al. Looked at 95 observations of coronal mass ejections, and they measured their kinematics. And so each of these double panels is a single event. On the x-axis, you have radial distance from the sun, from the surface of the sun, and on the y-axis, you have velocity and acceleration. So what can be seen from this is basically summarized here on this graph, showing that there is, for many of these events, there is an acceleration phase lasting for about half an hour, or until the CME gets to about 2 solar radii, and then the speed doesn't really change much after that. And something else that's interesting is that the acceleration correlates in general well with the hard X-ray flux, and the early stage of the increase of the velocity correlates with the with the soft X-ray flux. Something else that's interesting here is that the initial height of CMEs is quite low, as I mentioned, but it also correlates very well with starting times and frequencies or densities of solar radio bursts, which are taken to be indicative of shock formation and the presence of shocks in the corona. So in other words, we see shocks present very low in the solar corona. So the lower Alfvén speeds and the solar wind speeds of 20 kilometers a second or so, the relatively high densities which provide significant source of material to be accelerated, in other words, protons that can go to very high energies. The large gradients in speed of the CMEs in the densities of the coronal medium and the magnetic fields may be important for particle acceleration. Okay. So people started looking at, over the past, let's say, 15 years, people have started looking at what's happening in terms of acceleration closer to the sun, and of the behavior of CMEs itself and how they may accelerate particles, or do they accelerate energetic particles to high energies. So Manchester et al. Took a global MHD model, and they basically did a time-dependent simulation of a CME, and then they followed what was happening at the front of it. And so here they showed that there was indeed a shock that was forming very low in the corona, and that persisted over time. Koda et al. In 2005, they took some of these modeling results and they actually solved along single field lines. They solved the focus transport equation, which gives you the acceleration of particles, the change of the distribution functions over time, as well as the transport. And they showed as well that indeed you could have significant acceleration of particles, but this was still sort of new territory. People were looking farther out because of this paradigm of acceleration in interplanetary shocks. However, little by little, people were starting to look closer at what was happening near the sun. Okay. So me and my colleagues, we also did some work on this, and in a 2013 paper, we looked at the acceleration near the sun within 8 solar radii of a model coronal mass ejection. So here we used the so-called Batsa-Russ model, which was developed at the University of Michigan. And we recreated CME, and here you see the sun as a green ball, and the density contours showing the ejecta as well as the shock surface here. The black lines are the magnetic field lines going sort of out radially out of the sun beyond 3 solar radii or so. So when we look at the density, the first interesting thing is that over time the CME is deformed significantly. In other words, it doesn't follow an ideal shape over time, but instead it's deformed by coronal structure, and the density is different in different parts of the CME. This is a top-down view in the ecliptic, or in other words, an ecliptic cut, and this is a meridional cut. And the density and the magnetic field, of course, the velocity is different. Here you can see a side view that's showing the shock surface of the CME, which is quite uneven. Then the sheath behind it, followed by a pileup of density. The driver itself has much stronger magnetic field, and so the density there to achieve pressure balance, the density of plasma is lower. So you can see it very well in this. And then we took this simulation that had already been completed, and we extracted, in the same manner, we extracted individual field lines passing through different locations on the CME and in the corona. And so here in the bottom, I'm showing 6 different time steps for a single field line. So this plot here shows you on the x-axis a distance along the field line in solar radii. So it's not radial distance, but distance along the field line, because the field lines themselves can meander and wander around. On the y-axis, you have density. This is speed, magnetic field, Alfvén speed, as well as this metric that we use to locate the pileup of plasma behind the shock. So you can see the positions of the shock are also shown in these vertical dashed lines. So you can see the increase in density behind the shock as expected, of the speed, magnetic field. On the right here, these panels show you for each one of those time steps that we have plotted on the left. On the x-axis, distance along the field line. On the y-axis, you have energy. And the color coding shows you the enhancement, the log of the enhancement of the distribution function at each space and energy position over the initial distribution function. The red lines, again, show the positions of the shock. And so you can see in time the shock moves to the right, farther out along the field lines. And as the CME proceeds, the acceleration of particles proceeds as well. And over time, particles achieve higher energies and higher fluxes as well. And then later on, you can see that there is also escape in this V shape as the particles with the highest energies tend to start moving away from the shock, both upstream and downstream. So to do this, we used a similar approach as Kauda et al. From 2005, solving the focus transport equation. And so that really gave us confidence that there is significant acceleration that is possible close to the sun, maybe not so much very close to the sun, but as the CME exits these regions of higher density in the corona into lower density regions, and it basically takes over in terms of dynamics, and then that's when really the acceleration picks up. Okay, so global MHD and kinetic models are fantastic. You can see they give us a very detailed picture. We know everything about the system, and so we can play with it. The problem is that they're a little bit slower, and they're hard to constrain in terms of what is really happening on the sun. And also, they're very difficult to apply for routine multi-event analysis, especially at the early onset of CMEs close to the sun. So we can maybe try to use observations to constrain the acceleration of particles close to the sun and use such a model for multi-event analysis. But first, what do we need to model the acceleration of particles? Well, we need to know the kinematics, in other words, the speeds, the velocities that are involved. We need to know the strength of the magnetic field and the shock geometry, the density and the change in density, which gives you the shock strength, as well as the scattering conditions in the magnetic field, upstream and downstream. So let's start with the kinematics. As you saw before, we have these neat observations. By the way, the AAA cadence is 12 seconds, so there's an image every 12 seconds. It's just a fantastic data set. So we can use these, as I mentioned, to constrain the kinematics. We can deproject the system to make it easier, the data to make it easier for us to measure the kinematics, so we can look along this radial line. And then we can constrain the initial velocity. We have a second order polynomial fit and find what the acceleration is. So kinematics check. Okay. The potential field source surface magnetic model gives us a very good idea of what the magnetic field lines are doing. So these are coronal magnetic field lines that are based on an extrapolation from magnetograms, line of sight magnetic field observations. And apart from getting the local magnetic field strength, you can get the angle between the local magnetic field and the shock, the so-called theta BN, which is quite important in the diffusive shock acceleration models because it controls the scattering of the particles and the efficiency of acceleration. So we can combine the PFSS model with a 3D model for the surface of this shock wave and then follow it over time to see what the theta BN angle at every crossing here between this surface and the magnetic field lines from the PFSS model is. So you can see over time it changes significantly. We can look at the distribution with time of different ranges of theta BN, and it's very interesting here to note that this radial burst when the shock shows up in radio observations is when a little after there's a significant increase of the high theta BN angle ranges, which means a lot of acceleration is supposed to be going on. So you may say, how do we know these are shocks? Well, as I mentioned, there are several ways. First one is to look at the kinematics and then look at the alpha in wave speed, alpha in speed, and say maybe the alpha in speed, when it's moving faster than the alpha in speed, then it's a shock. Then there's the radio observations, and then there is the differential emission measure, which allows you to look along the line of sight and reconstruct the amount of material that's emitting in a certain temperature range. And the AA, since AA has many telescopes, 4 telescopes with different filters sensitive to different temperatures, it can allow us to do that. And so from such observations, we can get the density change in certain regions for these events. Ooh, okay, these are just movies. Just a movie of the emission measure, which is the integrated differential emission measure, and the maximum temperature that was reached. Okay, and we can look at the time series of these and tell something about what's going on. So this gives us the density change that we need. So we have the kinematics, the magnetic field strength, the shock geometry, density change. We don't really have the scattering conditions because we need in situ observations still to get those, so we make some assumptions. But anyway, with those assumptions, we can develop a diffusive shock acceleration model, and I won't bore you with the details of this, but there is a solution, and it depends on the spectra basically depends on the shock strength, which we can also obtain, and the amount of acceleration also depends on this angle theta BN, as well as the mean free path for the acceleration. So I'm currently this is some current work that I'm doing. I'm testing, we've built this model, I'm testing it, and there are 8 runs with different shock speeds, magnetic fields, same magnetic field. We haven't changed the theta BN angle. We used a quasi-perpendicular shock and a quasi-parallel shock, so very high, very low theta BN angles, and then the shock jump conditions, a very strong shock and a very weak shock. So here's a plot that's showing over time, these are different time steps, are color-coded, that you can see the integrated flux between 10 keV and 1,000 MeV. And so over time, the spectra in this range reach sort of a steady state, which, based on the diffusive shock acceleration models, in theory, you should reach a single slope, as I said, based on the strength of the shock. So in this case, this is line A. The slope of the spectrum should be flux to the energy to the -1, which is what we see here, of course, with some numerical changes. You can see over time how the spectra vary. So here we have 10 time steps, 40 time steps, and 80 time steps. The slope remains the same over time, which is also what's expected. So we're happy with the results here, except the shock has accelerated the particles to higher and higher energies. And then you can compare the total fluences of these, the first 4 and the second 4 runs. So you have, wherever you have high theta BN angles and high shock jumps, as well as high shock speeds, you have particle spectra extending farther out. And so you can see with 10 time steps, 40 and 80 time steps, that the spectra are formed to higher and higher energies. And the same is true also for the weak shock to a much lesser extent. So overall we're quite happy with the performance of the model, and the next step would be to apply this to real observations. Okay, so in summary, as I said, many CMEs, they reach peak acceleration within 2 to 5 solar radii, and this is a very interesting dynamic region that may be very important for the acceleration of particles. The CMEs are very often fast enough to drive shocks, and the shocks may become strong enough to accelerate the charged particles to tens or even hundreds of MeV. I know this may be low energy to you guys, but it's quite high for NASA, and so they're interested in knowing what's going on there. These recent global coupled modeling and data-driven approaches may give some significant insight into what we know about the particle acceleration. So they're helping this paradigm shift from acceleration in interplanetary shocks to maybe acceleration lower down near the sun. And they may allow us to make faster predictions for space weather, which are quite important for operational purposes. Thank you.
So in your first movie, like you showed ejection in the sun, like how much mass is ejected and what fraction returns to the sun?
Short answer is I don't know. It really depends because this isn't white light, and so you have these are line emissions, and so you don't see everything that's coming out. So I couldn't tell. I can refer you to some papers on this. This is a very famous event, but I'm not quite sure, unfortunately. Sorry. Yeah.
So did people ever localize this type 2 radio burst with the location of these shock things? Because that would be really a signature of like acceleration. Because this is kind of a photon bucket observation from the whole sun, where you see this radio burst, but can you localize them on top of these shock waves? Or is that really extremely hard because they're so dynamically like...
Yeah, so people have tried to do that, and there's been some observations, but those have been observations usually of emission within the flux rope itself, behind the shock. There are efforts right now to do. There have been some efforts to do this, and with some of the new radio telescopes like the Murchison Wide Field Array, LOFAR, people have started to look at the emission from the shocks, and I think we're very close to it. Actually, there have been some observations from the Nancy radio heliograph, but it's really difficult to do this because even then the frequencies change so quickly because of the density profile that it's just. Yeah. But people are trying, yeah.
So in the last model, you had two different examples. You had two different examples of the Mach number. So are you unable to distinguish that, or do you actually know the Mach numbers from earlier on when you were showing the outburst? You had a graph that showed the outphase velocity as a function of radius. But you actually know how strong the shocks are.
Right. So you could use the DEMs to try to figure out the density jump right, at the front of these UV wave fronts, and you could use kinematics as well as some sort of but you need some sort of a model for the density in the magnetic field to calculate the alpha speed, right? So that's also kind of model dependent, but you can do it. People find it. It's usually They're usually quite weak shocks that are sort of strengthening as they leave the field of view of AA. Unfortunately, it only extends to 1.3, 1.5 solar radius, so we can't follow them. But people have tried to do this with white light chronograph observations.
So was the 1.3 the more realistic number rather than the 4?
Yeah, yeah, I would say so. Of course, I haven't done this for many events, but there are faster waves and
In some cases, they reach Earth and they're actually measuring it. So they need deeper measurement.
right. So yeah, in some cases, but then you don't know, the shock strength, of course, may vary in time. But yeah, 1.3 is a more realistic, maybe 1.5, 1.8. Yeah. So weak shocks in general.
Any other questions? Again? If not, let's thank our speakers today.
Thank you.